Steinhauer here. Welcome back. Continuing discussion of the Milky Way and how we can use the speeds at which objects orbit within the Milky Way galaxy to determine the mass of the Milky Way itself. And we need to introduce a concept now that's going to be important in the weeks ahead, and that is something called a rotation curve. And a rotation curve is a plot that plots how fast an object is orbiting another object as a function of how far it is away from the center of that object. So for the rotation curve of the galaxy, it's how fast objects are orbiting the galaxy as a function of how far they are out from the center of the galaxy itself. You might remember way back in the beginning of the semester when we were talking about Keplerian orbits and Kepler's laws, I said, we made a plot like this, and I said, remember this for later in the semester. This is going to become important. Well, we've reached that point in the semester, so yay for that. But let's remember what that plot was looked like, because we actually did show that. Let's actually make it. We've got a plot with r on the x-axis and velocity, how fast stars are orbiting, on the y-axis. So we can actually see it here. We've got a diagram, a cartoon diagram of the solar system here. We've got the sun at the center. We've got, an inner planet like Mercury, the Earth, and an outer planet like Mars. And for Keplerian, for the solar system, the further you go out, the slower you move. So Mercury is moving pretty fast, and then Earth slower, and then Mars slower yet. So if you plot that, so here is Mercury is close to the sun, and it has a high orbital velocity. Earth is further away from the sun, and it has a lower orbital velocity. And Mars is further away yet, and it has an even smaller orbital velocity. So if you plot this for all distances, it makes a plot that looks kind of like this. If you're familiar with this, this is a 1 over r plot. V equals 1, V proportional to 1 over r. So this is what we call a Keplerian rotation curve. It follows Kepler's laws, and Keplerian rotation curves happen when all of the mass is located at the center. For the sun, you're not adding any more mass as you go out. It's the same amount of mass as you move away. We can actually understand why this is for the solar system. Remember, V circular squared is equal to gm over r, right? And m is how much mass there is inside of your orbit. If m is not going up, then the velocity is going down by a factor of actually the square root of r in this case, right? Because we could take the square root of both sides. V is proportional to gm over r. If m isn't changing, then v has to go down as you go farther out by 1 over r to the 1/2 power. And that's what this curve is going to look like. Okay, so that's the solar system. But let's, just to make sure you understand the concept, let's ask a concept question that involves a bicycle wheel. So here's a bicycle wheel, or you could think of this as a frisbee, or anything that rotates as a solid body. I want to know what the rotation curve of this thing looks like. It's spinning on its axis. The axis is here at the center, and it's moving as a solid body, meaning it's not slipping. These spokes are staying solid as it moves around. What does the rotation curve look like? How does the velocity change? So this is going to be orbiting in a different way, but for a different reason, but in the same way. These point on this spike is going to be orbiting around the center of that axle as the bicycle wheel spins. So what do you think it's going to look like? A, B, C, or D? Take a guess, and we'll talk about it. Okay, let's talk about a specific point on this curve, on this bicycle spoke. Let's say right there near the middle. That object, so in fact, let's think about 3 of them. We'll do one there, and one there, with 3 different colors, right? So so this bicycle wheel spinning around, how long does it take one of those points to go all the way around and come back to where it started from, right? It has to be the same for all of these. That one makes 1 complete revolution. This one, oops, let me do the right color. This one makes 1 complete revolution. I'm not drawing very good circles here, but you get the idea. This one makes 1 complete revolution. And those have to happen in exactly the same time because this thing is spinning as one. So these are not all moving at the same speed around the center, right? The inner spoke has to be moving slower. The inner point on the spoke has to be moving slower than points further out, because this one is traveling this distance in that amount of time. This point is traveling a much further distance in the same amount of time. And this one at the edge is moving a much further distance in the same amount of time. And so the velocity of this point has to be bigger than this point, has to be bigger than this point. And in fact, they goes up in a linear fashion. And so this one will look like this. It will be a fairly linear plot that will go straight up over time. Now, no gravitational object behaves like this, but this isn't an object that's orbiting due to its gravity. It's orbiting due to other angular momentum issues and is staying fixed in a solid body due to the forces imposed by the spokes in this particular case. The galaxy, though, the rotation curve of the galaxy, you might think it looks the same as the solar system, right? You've still got the force is gravity, and things are going around, and it looks kind of the same. Well, it doesn't, in fact, look anything like the galaxy. So that's very interesting. It turns out that objects orbiting the galaxy do so at about the same speed at all distances from the center. And so that's an interesting thing. Why is that? This is not a Keplerian curve. If we draw this out, it looks something like this. Again, this is R and this is V. Does some interesting things in the middle, but it kind of levels out and stays flat for large values of radius. And so this is what we call a flat rotation curve. What is different between the galaxy and the solar system? Well, let's think about what this equation is again. V squared circular is equal to G times M divided by R. So what is this saying? If this is flat, it means that M and R are changing in exactly the same way. It means that I'm encountering more and more mass. Remember, this M is M of R, really. It's how much mass is interior to your orbit, right? And so M increases as you go out, because unlike the sun, the solar system, where the mass is all at the center, the mass is kind of evenly distributed throughout the galaxy. We know that there's a supermassive black hole down here, yes. Actually, we don't know that. There are some massive things in the galaxy, but overall, the galaxy's 100 billion solar masses in mass. It's fairly evenly distributed. It's fairly smoothly distributed throughout the galaxy as a whole. And so as you move out and R gets bigger, M gets bigger too, in such a way that these two things cancel out. And after you get past the first, the inner part of the galaxy, this rotation curve flattens out and becomes fairly constant as you move out, which means that M is going up exactly the same way that R is as you move out. Okay, so that's interesting. And you can use the rotation curve of the galaxy then to tell you what the mass is interior to all of these radii and see how the mass is distributed throughout the galaxy. So that's cool. Now, but something strange happens, and this is where the story gets interesting. In the outer part of the galaxy, we would expect, let's say we've got a galaxy that looks like this. So here's the center of the galaxy. We know we've got some spiral arms going off in both directions. And if we make this is basically what the plot is, right? You've got radial velocity or orbital velocity as a function of how far you are from the center of the galaxy. So this is kind of showing you at each of these positions, obviously R equals 0 is the center of the galaxy, how far you are moving out. Well, we know how it looks to this point, right? It looks kind of flat going out. What would you expect the curve to look like after you get out past where we see the stars being the Milky Way? Let's say we've got some random object out here that isn't really part of the disk, but we measure its velocity. What would we expect to happen out here? Well, naively, we would expect that this would drop off again, right? Once you get outside the majority of the mass of the galaxy, it should behave somewhat Keplerian. If the mass truly stops here, we would expect the Milky Way rotation curve to fall off as that 1 over square root of r did before. We would expect it to get smaller as we move out. In fact, it does not. And this is interesting. In fact, here is the true rotation curve of the galaxy. You can see it stays fairly flat for a large range, and you got some wiggles here, but it stays fairly flat for a large range of radii. This is sort of where the visible surface of the galaxy ends. The visible disk of the galaxy ends here. We would expect this to fall off in a Keplerian-like orbit if there were no matter out. So the fact that the rotation curve of the galaxy increases beyond the observed limit of the galaxy must imply that there's a lot of mass out there. There's only one way to get the rotation curve to go up, and that is that you're moving past even more mass. There must be a lot of mass out there. Okay, it's even worse than that, though. If you add up all of the visible matter that you can see, even within the sun's orbit, all of the stars, all of the gas, all of the dust, all of the molecular clouds, everything that you can see or even infer that it's there based on the fact that you can't see things behind it, you only get to about 10 to 15% of the mass that you need to explain the orbits of stars like the sun, and even worse as you go out. That's a real problem, right? 85% of the mass of the galaxy seems to be missing. We can only see about 10 to 15% of it. That's a real problem. So what is this stuff? What do we call this stuff? We actually don't know what it is. Could it be brown dwarfs? Could it be black holes? Could it be neutron stars? These are all things that have mass that don't emit much light. Could they be, I mean, there's all kinds of possibilities for what this is. We don't know what it is. That's the real answer. It's kind of embarrassing that in this modern age, we don't know what 85% of the universe, what of the galaxy is, but we call it dark matter. Dark because as a metaphor for us not understanding what it is, and also dark because whatever it is not emitting any light at all. It doesn't seem to interact with light at all. So possibilities for what this R is endless. We will talk about some possibilities in more detail later on. But that is the state of things. We don't know what 85% of the galaxy is. Okay, I'll stop there in this video. We'll come back in the next one and talk about the monster that lurks in the very center of our galaxy. See you then.